Hey guys, Mr. Barnes here again, bringing another math video. In this video I'm going to talk a little bit about trigonometric limits. So you've probably done a bunch of different examples of trigonometric limits in your calc classes and you're like, oh my god, how am I going to figure this out? Well, I try to keep it really simple for my students, and there's nothing simple about trig in any form, but for trig limits we can kind of break it down to 5 different things that we need to remember. So first and foremost, we need to remember this guy. The limit as x approaches 0 of sine x over x is equal to 1. So this is one of those limits you absolutely need to know. If you're looking for a proof of this guy, you're not going to find it in this video. I tell my students, yeah, it's important to sort of have an idea of where this comes from, but it's more important to be able to use it and actually just know it and apply it to solving questions. So the next thing I tell my students that they need to know is that the limit as x approaches 0 of just sine x is equal to 0. And that's just direct substitution. Sine of 0 is just 0. Now the other one, which is sort of like, the pretty cousin of this guy, which a lot of my students prefer, is the limit as x goes to 0 of sine kx over x. So that's when we have a number times sine. So any number, or just not times sine, inside the sine function. So times the x, or the variable inside sine, and that's just simply equal to whatever that number is. Alright? So that's a thing of beauty right there. So it's equal to whatever that number is. So I would caution about using that rule, but my students absolutely love it. So if you're in calculus, you might want to say, sir, you might want to mention to your professor or your teacher, say, sir or miss, can I use this law in solving a proof? To me, I'm all for it. So I'll kind of take you through using this law in particular, and maybe I'll do an example where you don't use a law. Alright, so now let's look at cos. So the 2 proofs we need to know with cos is that as x approaches 0 of cos of x, that's just equal to 1. So again, that is just direct substitution. Now the other limit that we need to know with cos is the limit as x approaches 0, cos x minus 1 all divided by x, and that's equal to 0. So this is another one, there's a proof involved, but again, the video is not the purpose to be able to show those proofs. It's just simply to be able to use and apply these 5 limits, not derivatives, and actually use them to solve problems, because ultimately that's what you're concerned about, unless of course your teacher says you got to know the proof of that, I could ask it on a test. Which I haven't seen on very many calculus exams. So let me do an example now of using by far the most popular thing that you use with a proof. So let me just do a question. So x is equal to the limit as x approaches 0. And a lot of times you'll see 0, anything other than 0 here, guys, and I'm getting really curious why it's not 0, and maybe I'm applying direct substitution to it. But I know if I apply 0 into any of these forms, I'm going to get indeterminate form. So if I put 0 into this, I'd have sine of 0, which is 0, over sine of 0, which is also 0, and then, I'm flat out of luck. So I'm going to do this question 2 different ways to show you the two different mindsets of how to do a question like this. So I'm going to do it my way. I always ask myself the question when I'm doing limits like this is, how can I make every single thing in the limit that has a sign in it look like sine kx, so in our case 4x or 6x over x. So what is this guy missing? What is this guy missing? Well, it's missing the divide by x. So remember, we could do anything to this guy as long as we do the same thing to the top and bottom. So I can multiply it by any number, I can divide it by anything, any variable, whatever I want to do. So I'm going to divide the top and bottom by x. So the limit as x goes to 0, so I'm going to say sine 4x divide by x, all over the sine 6x divide by x, just like that. All right. So now I can say, well, I can use my rule. I know that the limit of this guy is just equal to k, so this guy would be, well, I'll rewrite this step. The limit as x goes to 0, sine 4x over x, and then the limit as x goes to 0, and then we move it up a bit, sine 6x over x. So, you know, I can do this limit right here. Of course, that's just simply 4. And then this guy, the limit right here is 6. So that reduces down to 2 over 3. All right. So let's try this limit in a slightly different way. So let's try it using what I call the annoying way. I don't know what your calc teacher might be saying. It's the right way. That's the way I learned it in school. Well, that's fine, but this is the way I learned it. So whatever works for you, that's what I say. All right, so usually what I see a lot of old school teachers doing is trying to get things in terms of if there happens to be a 4x here, trying to get things in terms of 1. So everything to work out to be 1, all your limits to be 1. So you want to sort of get, you know, sine of kx over kx instead of just x. So let me show you what I mean by that. So if I have a 4 and a 6 in here, I have to think about either a common denominator or something like that. So the common denominator of 4 and 6 would be 12. So instead of dividing by x, I'm going to divide by 12x. So I get sine 4x over 12x, and then sine 6x over 12x. So I divided the top and bottom by this particular thing. So now what I'm going to do is I'm going to break up this 12 into 3 times 4x. So I'm going to keep the 4x with the limit and take the 3 to the outside. So I'll write, and I'm going to apply this limit to both things now so I can kind of take a shortcut. So the limit, oh, I already got a limit there, sine of 4x all over 3 times 4x all over limit as x approaches 0, sine of 6x all over, and then that 12x breaks up into 2 times 6x. So this guy right here, and then this guy right here, those are actually 1. Okay? So what I end up with is the limit. Actually, I don't. Yeah, I'll rewrite my limit sign. So what I'm going to do is I'm just going to sort of differentiate this a little bit. So 1 over 3 sine 4x. I did it again. My bad. And then the limit as x goes to 0. 1 over 2 this time of sine 6x over 6x. So this guy right here, that is 1, and this is also 1. You might be asking yourself, why is it? Well, essentially, we kind of think of this almost like this. If this was just u and this was u, it'd really be no different, right? Like if this was just something other. So these two things are the same. As long as you're matching what's inside the sign with what's in the bottom, it's going to be 1. So that's sort of the beauty of this thing. But I mean, it doesn't be the beauty of this. This thing is magical. So anyway, what you get left with is 1 over 3 divided by 1 over 2. So then we can flip and multiply that, and we get 2 over 3. So we get the exact same answer, but you know, you can see how a little bit more complicated that is. So whatever your teacher prefers, that's what I would do. So guys, just a little introduction to, you know, getting the idea of trig limits. So with your, you know, 5 things that you need to remember, basically what you want to do is make them look like this. So make them look like this and then see where it goes from there. Alright guys, thanks for watching. I really appreciate all the effort that everyone puts into their math. Anytime you got any questions, drop me a line on Twitter. I'm at Math Mr. Burns. I am the least popular math teacher on Twitter. I'm sure of that. So hit me up, give me an ad shoot me a few questions, and I'll certainly get back to you. All right, guys. Thanks for your help. See you guys in class.